All right, so we're going to look at an example using the relationship between position and velocity that we've talked about at the end of the previous video. So there's two parts to this. Suppose an object is dropped from a 500-meter tower. We want to do two things. We want to find the velocity of this object after 3 seconds, and then we want to find how fast the object is traveling by the time once it hits the ground, that exact instant in time. In order to answer either of these questions, we need to use something we've already come up with previously. This, S of t equals 4.9t squared. This is the position function for an object that is in free fall that was dropped from rest, basically. So we didn't apply any initial velocity to it. We're just holding it in the air and then dropping it, essentially. We don't need to talk about where this came from because we already talked about it in the past, but this is our position function. Up here we're calling our position function f, but typically it's called s, so I'm going to be changing the notation a little bit. Okay, we need this. So for part A, it says, what is the velocity of the object after 3 seconds? Well, up here we have a little formula involving a limit that tells us the velocity in terms of our position function. So v of a, in this case specifically, we're looking for v of 3. That would be the velocity of our object at time 3. That's equal to, according to our formula up there, the limit as h approaches 0 of f of 3 plus h. So that's the same thing as this, 4.9 times 3 plus h squared, okay? Minus f of 3, or 3 squared. 4.9 times 3 squared. Sorry, let's put a little 4.9 in there, okay? All over h. Now there's a 4.9 showing up in each of these terms here, which I can factor out, and by our limit laws, because it's a constant, I can factor that all the way outside of the limit. So this is equal to 4.9 times the limit as h approaches 0 of 3 plus h quantity squared minus 3 squared. But let's go ahead and expand that out. So 3 plus h squared is 9 plus 6h plus h squared. And then this 3 squared here becomes 9, so minus 9. All over h, okay? So that's what I've managed to simplify so far. I now see that I have a 9 minus 9, which could cancel. And then all of my remaining terms have an h in them. So I could factor an h out of these two terms and use it to cancel with this. Or I could cancel that h individually with a single h from each of these terms. What does that leave me with? 4.9 times the limit as h approaches 0 of 6 plus h. That's what's left. Okay, over 1, but I don't need to write the over 1. It's the same thing as just 6 plus h. Now I have a polynomial in here, or a linear function, continuous everywhere, so I can use direct substitution to evaluate this limit. Plug the 0 in, and I get 4.9 times 6. That's what this limit would be equal to. This is equal to 4.9 times 6 comes out to 29.4. And this is a velocity, and this specific form of our position function assumes that our units of distance are measured in meters. So this would be measured in meters per second, okay? That's how fast this object is traveling 3 seconds after it was released. Now for part B. Part B says, how fast is the object traveling when it hits the ground? In order to answer that question, we first need to know how much time elapses before it hits the ground. And to do that, we don't need a velocity function yet. We will need one after we determine this first step. We just need our original position function. So this, remember, gives us how far the object has fallen at a given time t. But we know how far it should have fallen when it hits the ground. It's a 500-meter tower. So S of t should be 500. 500 equals 4.9 t squared. What would t have to be? This is straightforward to solve. Divide both sides by 4.9, take a square root, and we get this. T is approximately 10.1 seconds. Okay, you can verify that. That's a really easy one to solve. Now, what do we need to do? Well, the next step would be to use this 10.1 in our velocity function. Okay, so now what I need to do is find the velocity at that time when this object is hitting the ground. So v of 10.1, this would be equal to, using my velocity formula up there, the limit as h approaches 0 of 4.9 times 10.1 plus h squared minus 4.9 times 10.1 squared. Okay? All over h. Now I want to point something out here. I'm not going to go through all the same steps as before. It's really important in math specifically to start picking up on patterns, because that's going to help you save a lot of time, helps you be efficient. So when we evaluated this velocity function, or this v of 3, how does that compare and contrast with what we're doing down here, v of 10.1? Well, the expressions look almost the same. The only difference is that where I had 3's showing up here, I'm having 10.1's show up down here. Okay, so I know a few things are going to happen. For one thing, I can still factor that 4.9 out. 4.9 times the limit as h approaches 0. And now I'm going to look at some patterns here to try and see if I can eliminate a lot of unnecessary work. So after I expanded this guy out, I ended up with 9 plus 6 plus h squared minus 9. These two constants ended up canceling each other out. And it's not hard to see that the same thing will happen here. When I expand this, I'm going to get a 10.1 squared. And here I'm going to end up with a minus 10.1 squared. So those constants are going to cancel out. I don't need to actually evaluate 10.1 squared to know that that's going to happen. What's left is a couple of terms from my polynomial. And this 6h, the coefficient here is exactly double that constant. The same thing's going to happen here, and hopefully you can see why that is. So instead of 10.1, I'm going to end up with 20.2 times h, but then that h will eventually cancel out, plus h squared, but one of those h's cancel out, and I get plus h down here. Again, if you need to do all the work that comes in between those two steps, by all means do it, but it's going to look essentially identical to what we already did in part A, just with a few numbers looking different. The pattern is there. So as h approaches 0, once again, this h will go to 0, giving me 20.2. So this is equal to 4.9 times 20.2. Just use a calculator for that. That's going to be approximately 99 meters per second. Okay? Cool. Let's go ahead and move on. All right. So at this point, we've seen that limit, that same limit appear in a couple of different contexts. That's what I'm saying up here. So the slope of a tangent line, but that exact same limit, the limit as h approaches 0 of this difference quotient, also represents instantaneous velocity if the function f represents a position function. And this same limit with that difference quotient is going to appear in many other contexts that we'll look at. So it's clearly something very important. Because it's so important, we give it its own name. This is the derivative. So this is our definition here. The derivative of a function f at a number a, which is denoted by this notation. That little apostrophe right there, we read by saying prime. So when I see this, what I'm saying is f prime of a, okay? The derivative of f at a number a, which is denoted by f prime of a, is this. The exact same little formula that we've already been looking at, but now we're calling it a derivative, okay? And again, this is always assuming that that limit exists in the first place. So we could alternatively define the derivative this way. Remember, at the very beginning of this section, we saw this definition for the slope of a tangent line, and it gives you the same thing as this. So these are interchangeable. Either one of these could be used as our definition of a derivative, but in most cases, this is the one we're going to use. Okay, for the purpose of simplifying these difference quotients when evaluating the limits, this one tends to be more useful. So I'm going to be sticking to this. Okay? All right. So let's try an example. I want to find the derivative of f of x equals x squared plus 3x minus 6 at x equals 1. Okay, so that just means I'm finding f prime of 1 using this formula here. F prime of 1, what would that equal? That's equal to the limit as h approaches 0 of, going back up here, f of 1 plus h. But we have a function here. So let me actually use the function notation. F of 1 plus h minus f of 1 over h. Okay, what does that equal to? Limit as h approaches 0. F of 1 plus h is whatever I would get from plugging 1 plus h in for all of the x's in this function. So that's going to be 1 plus h squared. Plus 3 times 1 plus h minus 6 minus f of 1. This is a really important thing to pay attention to. Make sure that you do what I'm about to do. I'm gonna be putting this entire expression in parentheses. Okay, so f of 1 would be 1 squared plus 3 times 1 minus 6. The reason it's important to put that in parentheses is because you are subtracting the value that we get from plugging 1 into f. If you leave these parentheses off, you're not subtracting f of 1. You're only subtracting the first term of that expression there. This is a common mistake that people make. If you fail to put these parentheses around this second part here, specifically in the cases where there's more than one term to deal with, you're going to get the wrong answer. You have to remember these parentheses. Okay? All over h. Now it looks like I have a lot of simplifying to do, so I'm going to work through that. This is equal to the limit as h approaches 0. 1 plus h quantity squared is equal to 1 plus 2h plus h squared. Distribute my 3 in here, plus 3 plus 3h minus 6. And then what is this all equal to? 1 squared plus 3, that would be 4, minus 6, that would be negative 2. All over h. All right, let's look at simplifying some things here. So I have, actually, hold on. I made a little mistake. I want to correct that first. So 1 squared plus 3, that's 4. Minus 6 is negative 2, but we are subtracting negative 2, which makes that a positive 2. Again, I have to remember that's kind of the reason I have these parentheses here. I'm subtracting that entire quantity. So now looking at what's left, I have a 1 plus 3, which is 4, plus 2, which is 6, minus 6 is 0. So all of those constants canceled each other out. Super convenient. Now, if you notice, the only terms that remain, 2h, h squared, 3h, h, all of those have an h in them. And so I can cancel those h's out. I could have also combined these two terms, but I'm going to do this first. Cancel h's out of everything. Now what's left? Well, I have a 2 plus 3 here. That's a 5. Plus one of the h's from this h squared was left behind, so that would be plus h. And then this h canceled out. That's gone. So my entire somewhat complicated looking expression simplified down to something much nicer looking. In fact, it's a linear function, so I can use direct substitution again. Plugging 0 in for h gives me 5 plus 0, or just 5. Okay? And that would be f prime of 1. It's equal to 5. So not too bad, right? It's just you're doing a lot of algebraic simplification. But if you're in calculus, algebra should be no problem for you. If you're struggling with things like this, for example, like the fact that I knew that 1 plus h squared was equal to 1 plus 2h plus h squared, I knew that without having to FOIL, like the way that you learn in elementary algebra. If you have to take the time to set up FOIL and do all of the kind of really basic algebraic manipulations, I'm just gonna be honest, you're gonna have a hard time in this class. You have to have mastered that if you're here now, if you're in Calculus 1. Let's keep going. This time I want to find f of x, or sorry, given f of x equals the square root of x, I want to find f prime of a, where a is some positive number. A has to be positive because this function is not defined for negative numbers, and it is defined at 0, but we're going to be assuming a is just strictly positive for this case. What's different about this is I'm not specifying a value for a. I'm leaving it general, right? In the previous problem, we found f prime of 1. I used a specific number. Here, it's just being called a. And this is going to be kind of a preview of what we're doing in the next section. It's much more useful to not assume a specific value here, but to keep things general. So what would f prime of a be? Well, by definition, that's f, sorry, I forgot my limit. It's the limit as h approaches 0 of f of x, a, sorry, not x, plus h minus f of a all over h, okay? Which, using our definition of f up here, this is equal to the limit as h approaches 0 of the square root of a plus h minus the square root of a all over h. And as we've seen in the past, evaluating limits involving radicals like this are oftentimes best evaluated by multiplying using a conjugate. So a plus h, the square root of a plus h plus the square root of a over the square root of a plus h plus the square root of a. So it's my multiply by 1 trick. Very, very useful for limits. Okay, in my numerator, this is going to come out to a difference of squares. So limit as h approaches 0. I'm going to end up with this quantity squared minus this quantity squared, which of course would just be a plus h minus a. Down in my denominator, as we've seen, it's better to leave the product of these two denominators in factored form. H over the square root of a plus h plus the square root of a, because you're going to get cancellation. That's easier to see if you leave it factored. Notice my a and minus a canceled each other out. All I have left up here is an h, which will cancel with this h down here. That's going to leave me with a 1. So now I have the limit as h approaches 0 of 1 over the square root of a plus h plus the square root of a. Okay, now at this point, if you notice, direct substitution doesn't cause a problem for me, because h, if I plug a 0 in for h, that's just going to leave me with the square root of a here, whereas I'm adding another square root of a. Neither of those are equal to 0 because we're assuming a is greater than 0, so the sum of those two things would be some positive number. I'm not dividing by 0, no problem there. This is equal to the limit. Sorry, actually, let's evaluate the limit. Let's put this up here. I'm going to evaluate the limit using direct substitution. So this is equal to 1 over the square root of a plus the square root of a, or to simplify things, 1 over 2 times the square root of a. Now I want to point out the benefit of this approach. Suppose we were doing some kind of a problem which was looking at the function f of x equals the square root of x, and we needed to find the slope of various different tangent lines along that curve. Maybe we needed the slope of the tangent line where x equals 1, 2, 3, 4, and 5. That's like 5 different slopes that we're trying to find. Notice that if I wanted to do it using the original formula every time, I would technically have to go through all of this work 5 times for each different value of a that I was computing. But instead of plugging in a specific number at this stage, I kept things general, and I found f prime of a giving me this expression right here. What this means is that for any of those values of a where I'm trying to find the slope of a tangent line, I can instead just plug it directly into this little formula, and that'll spit out slopes for me for whatever I want to plug into it. It's much faster and much more efficient, and that's the idea behind what we're going to be doing in section 2.8. So this is kind of a preview of the last section of chapter 2. Okay, but let's just continue moving along here. So we've looked at one example of the derivative as it pertains to position and velocity. Specifically, what we saw back in, where was it? Back on this page, in light of our definition, the velocity function is the derivative of the position function for a moving particle. So that concept is a specific case of a much more general idea, which is that derivatives represent rates of change of a function. Okay? So in the same way that velocity is the rate of change in position with respect to time, other functions which have an independent and a dependent variable can be thought of in terms of their rates of change, and the derivative is going to represent rates of change in there as well. So we're going to use some notation here to sort of flesh out this idea. And first of all, suppose that we have some function y equals f of x. So y is a function of x. X is my independent variable, y is my dependent variable. What we're specifically interested in is changes in x and corresponding changes in y. The word change is used a lot in math, and calculus specifically. And what we mean by that is if we take, for example, a change in x, as we move from one x value, say x1, to another x value, x2, the change in x is defined to be the amount by which x changed, going from x1 to x2. The way that we're going to define and notate that is by using this symbol. This triangle here is the Greek letter delta. So I would read this as delta x equals x2 minus x1. I just referred to that as the change in x, but another term that we use a lot is increment. So we can define that as an increment in x. Now, as I move from x1 to x2, my dependent variable y is a function of these x values. So there's a corresponding change that happens in my y. So naturally that we use the same notation, an increment in y, a corresponding increment in y, we would call that delta y. And that would be equal to f of x2 minus f of x1, which you can kind of see from this diagram y is defined that way. So if I wanted to find an average rate of change in my dependent variable y with respect to my independent variable x, being a rate, we construct a quotient out of that. It's defined to be delta y over delta x, or this, f of x2 minus f of x1, all over x2 minus x1. And this is starting to look a lot like our original definition of the slope of a tangent line, which we can see from this diagram why it would look that way. So we end up moving from this, which is algebra, into the realm of calculus when we apply a derivative to that. So if we take that quotient, that average rate of change, and apply the limit as delta x goes to 0, which would look like this, then we're taking this from an average rate of change into an instantaneous rate of change. And again, the rationale behind making delta x approach 0 is the exact same as letting h approach 0 in our previous definition of the derivative, because delta x is just another label for h in that definition. So this is how we define our instantaneous rate of change. It's the limit as x2 approaches x1 of f of x2 minus f of x1 all over x2 minus x1, or the limit as delta x approaches 0 of delta y over delta x. And really, this is just an alternative definition of the derivative, which, again, we had another definition for, which we could also use. So to summarize that, the derivative f prime of a is the instantaneous rate of change in y, which is defined by this function, with respect to x when x is equal to a. Okay? So in this next example, rather than try to compute a derivative and an instantaneous rate of change directly, we're going to be more concerned with interpreting this. So let's suppose h of t, represents the daily cost in dollars to heat an office building when the outside temperature is T degrees Fahrenheit. Okay, so it makes sense that these two variables would be related. The higher the temperature outside, the more work that the air conditioning units are going to have to do to cool the office, and so it's naturally going to cost more. There's an expectation that those two variables are related somehow. We don't know how they're related. We don't know if it's a linear relationship, an exponential one, or something completely different. We just know that there's some function that relates those two. So there's two things we want to do here. First, we want to interpret the meaning of h prime of 58, and we also want to determine what the units of that are. Okay, so what does h prime of 58 mean? Well, this is talking about a derivative, specifically the derivative of the function h when t is equal to 58. Now remember, t represents degrees Fahrenheit. So right away, the fact that there's a 58 in here means we're looking at the value of this h prime thing when the temperature outside is 58 degrees Fahrenheit. But what does h prime mean in relation to h? Well, h prime, or the derivative of h, is the instantaneous rate of change in my original function, h of t, with respect to, here we're calling it x, but here the label for our independent variable is t, with respect to t when t is equal to 58 degrees Fahrenheit. What is that rate of change? Well, it's the rate at which the cost in our, the cost of heating our office building is changing at that exact moment, or at that exact temperature. So h prime of 58, and I didn't specify what it's equal to. I could have done that, but h prime of 58 would be equal to some number, is the rate at which the cost of heating the building is changing when it is 58 degrees Fahrenheit outside. Okay? B. Now it says, would you expect h prime of 58 to be positive or negative? So what does a positive rate of change indicate, and what does a negative rate of change indicate? Thinking about velocity, we've made sense of both positive and negative velocity in terms of positive and negative displacement. And this is not velocity, but it makes sense that we should also have a corresponding idea of negative rates of change and positive rates of change. So in general, a negative rate of change indicates that our original function is decreasing. It's getting smaller. Whereas a positive rate of change, or a positive derivative, would correspond to an increase in that function. So now let's think about this. We're not, I think I said cooling before. What I meant to say was heating. It says that we're heating an office building. If it's 58 degrees outside, do you suspect that we are going to be heating the building or cooling the building? Well, 58 degrees Fahrenheit is usually too cold for most people, and so we would be heating the office building at that time. Of course, heating the office building means we want to increase the temperature, and an increase in our temperature means we're increasing h of t, which would correspond to a positive rate of change. So positive because we are increasing the temperature. And I underline increasing because that's a very, very important correlation to make between a function and its derivative. If a derivative is positive, that means that the function is increasing at that instant. If it's negative, it's decreasing at that instant. And we're going to explore that idea in much more detail later. But for now, this is going to be everything we need to talk about for this section.